Well, we are going to continue then with the importance of functional groups in medical chemistry to be able to go into pKa acid base of base pharmaceutical type molecules. Then this problem that we have here is going to serve us to be able in some way, the introduction, so to speak, to go into the topic of pKa, which is what interests me. Yes, that is simple, I know, with so much acid. Well, there we are going to see how simple it is applied to biological systems. Then first, let's see some problems to start with. It says based on the following structures of medicine it responds. Then several molecules are shown. This is a table with several structures. And it says, for example, it orders a decreasing acidity. The compounds 2, 3, 4, 6, 7, then it says 2, 3, 4, 6, and 7. Okay, it says. Of basicity, I think it says no. Of acidity, decreasing acid, which is the most acidic. Well, first we are going to define yes. Before we are going to remember something very simple, and it is that in medicinal chemistry, the concepts are equated to the following. We talk about an acid. An acid, when we have a species that can give up a proton in the middle of a chaos, that is the classic definition, the definition of Bronsted, the definition of Arrhenius. They said that. And the acid group, par excellence, the carboxylic acid, it can give up a proton in the middle of a chaos. But what happens, for example, ask if you have the following. And hydroxylamide. You will see that group so strange in particular, of course, in some antitum. In fact, we have this group in particular. So if we think here, okay, this can give up a proton, of course. Which proton? What do you think? Because in acid groups, there are several in medicinal chemistry, there are several acid groups, not only one, but you have to see what is the critical point of the structure capable of giving up the proton, because in that atom there will be a charge, and when they do the docking we need the charge to be there, and not in the wrong atom. So what happens here? We have two possible candidates, the NH and the O. The NHA a little less, okay, that would be one thing. The second has to do with the nitrogen being directly connected to a carbon group. So when one has this type of, let's say, alternatives, one has to think who stabilizes the negative charge better. So when this dissociates, it prefers to release the proton over the nitrogen. Why? Because this way it stabilizes the negative charge better by resonance. So we are going to have a better stabilization by resonance. Okay. That's nothing new for you. It's something that resonance, if the NH, the base conjugated, stabilizes better, then that atom is the most acid. And when we talk about the acids in medicinal chemistry, we always have to think that a kind of acid in medicinal chemistry is the one that liberates proton. And what is the cellular pH? What is the physiological pH? It is not true, it is clear. The physiological pH is approximately 7.736. Well, let's round it to 7. So for an acid to be significant, for an organic acid molecule to be significant, in medicinal chemistry, I mean significant, when it is going to be ionized. When should we worry when its pH value is what range? Because, for example, what is the pH of a carboxylic acid? There we are trying to remember a concept that at some point in the past you must have seen it, which is the concept of pH. And today we are going to delve into this, the pH of a carboxylic acid is that we can approximate it to more or less 5. Very well. Then when we have a pH below the value of the physiological pH, that implies that the species is going to release proton. That is, it is going to be. Then this is supercritical. If we have a pH below the pH value, we have release of the proton, and that is a relevant acid for how much it is going to be ionized, you will say, to any value below 7, so that there is a 100% ionization, we have to be below 2 units. Then there have to be 2 units of difference. Then if we talk about a 100% ionization, a 100% ionization necessarily implies that there are going to be 2 units of a difference, that is. Here the pH minus the pKa is going to give us, it is going to give us as a greater or equal to 2, we are going to have 2 units of difference or more, and there the acid is relevant. Question: what other acid function do you know? Does any other come to mind? For example, with sulfur? Let's see. But the functional group, for example, I am already helping you here. A piece of the functional group is in some structure of pharmacist type. This is called sulfonate. Very well. This is a sulfonate. And it is a sulfonic acid when it has an H. Then there we have the acid proton. In all the cases to go marking this would be an acid proton. Acid proton. Acid proton that will be delivered to the medium. Then this is the definition that we use the most in medicinal chemistry. Definition is that of Lewis acids, but that is applied more for reactivity. Species that they have, for example, someone could tell them, well, that is an acid, yes. But also conceptually speaking, and this is not common in medicinal chemistry to have, for example, a drug that has aluminum. That is not because it is super toxic. But for example, look at the trichloride. I insist, this no longer has a direct relationship like that. But the aluminum trichloride, because it is an acid, that will not release any type of proton. But what definition applies there? The definition of Lewis is an acid of Lewis, because what is the thing going around? The classic definitions, such as the definition of Bronsted or Rhino, always talk about transfer of some particle as a proton or a hydroxyl group in the case of the bases. But when we go to Lewis, he talks about orbitals and electronic pairs. Then the aluminum is an acid atom. It is a center of acidity by how much it has an empty. Then we have an empty orbital. That orbital is an empty p0 orbital. Then the acid is the species that has an empty orbital. And the acids of Lewis, the truth is that they occupy themselves a little bit as drugs, due to which, because we cannot, it is rare. There are situations, it is debatable when one, for example, says that platinum is a drug and it is a metal. Okay, of DNA released to the genetic material, that does not necessarily have to do with the fact empty orbital. But the problem is that Lewis acids, that is with empty orbitals, are very easily linked to proteins, to carbohydrates, genetic material through that empty cavity, in quotes that they have, and that is why they cannot be used as a drug. They are too toxic, too reactive, and then that with respect to the acids from there, we are going to see they are going to make their way to walk, because a group that can release proton can be of several types too. See how is the short-term memory? Last week we saw vitamin C, and they say, yes, it is acid. We have all consumed vitamin C. What was the acid functional group of vitamin C? And a hydroxyl. Okay, then, in the case of vitamin C, the function was called enol. Once a double link, and well, there were 2 hydroxyls, but remember that one was only the acid. And this continues to there, continues to here. What was the acid? And the B is not true. because the one that is more exact, the one that can conjugate the ionic charge, the proton is released, then this was an acid proton in the structure because by resonance in this carbon-like unsaturated alphabet system, that is a Michael type system. Well, so that there they go refreshing the memory, and now as you can see, then there are many groups that can release a proton to pH 7, and they will have negative charge. Bases, and there the situation is different. And acids, there is a great variability. I am still not talking in terms of pKa with so much depth, only at the structural level first bases. In medicinal chemistry, the pharmacists, I would say that 90% of the pharmacists are bases. 90% of the pharmacists are bases. That is, they are structures of type. For example, when they are natural compounds, they can be alkaloids, or when we talk about synthetic molecules, we talk about, that is, the basic functional group, which is the basic functional group. A basic finger. Amine, well, perfect. Then amine is a basic functional group. The amine is the basic functional group par excellence. Then a drug that has a protonable nitrogen. Ron R2R3 is a basic drug that is a protonable drug, protonable to pH 7 OK, and we are remembering some things because today we are going to do numerical exercises of this. The pKa of amine is around. Someone remember what happens is that in the case of the amines, of course it will. Depend, but we can make a good approximation around 9, and there may be more base. Of course, yes, that is 11 more above, so they could have already, but a common and correct mine is around 9. And as we saw, that there are many possible acids, structurally speaking, what happens? With the case of the amines, there are also several possible amines or other possible functional groups. When you go to the periodic table and see group 5, what do you see there? Well, we have nitrogen. After what is under the nitrogen, this group 5, next to the oxygen. No longer true, but under the nitrogen. Be careful, the boron is here. Boron, carbon, nitrogen. And under it is the phosphorus, and under the phosphorus, the arsenic, the sulfur is here. Next to it, and well, the thing is that because I study, the intention is no longer annoying with this type of questions like that, but that they come here to reasoning. And that now let's say, okay, if nitrogen is a base, it could have a basic phosphorus. The truth is that it is very unlikely, okay. There are some cases, and I am going to show you a phosphorus has the same valence, that is, the phosphorus can also exist in this way, so Ron R2R3, and these molecules are called phosphine. But the truth is that they are not very basic, except exceptions, and there are phosphine. They are avoided as drugs because a rare phosphine that is a drug is not going to be used as drugs. What is the reason? What happens with the phosphorus atom? In the past, in some particular discipline, when they studied some toxicology related to it, they saw that there are many phosphorus molecules. For example, insecticides, phosphorus organs. I feel that they are toxic, and that the phosphorus is what is known as a strongly oxophilic atom. The phosphorus-oxygen bonds are one of the strongest in chemistry, and the energy of the very high units costs a lot to break it. Has a very strong thermodynamic tendency to see oxygen and capture oxidation. That in fact, the phosphine is used to extract oxygen from organic molecules. Then the rare phosphorus will be in the structure of a drug, except in particular situations, for example, drugs of utopian use. There are, if, for example, there are certain colorists that are phosphorus organs for the treatment of glaucoma, but they are applied in the eye and the effect, a systemic effect, or the damage would be serious, then be careful with that. Therefore, if you ask them and what other drug, what other group is going to be basic in the case of drugs, the truth is that we do not have more options for the case of drugs. The base is by excellence and amine, and so the bases are amine, as I tell you, basic phosphorus theoretically. Someone will say, it has the electronic pair, yes, but it is not very good to exceptions now, because it is not good to protonate. The explanation is phosphorus is much larger than nitrogen, and therefore its retention capacity of a proton is smaller. This electron cloud here, this orbital, with this pair is large and makes a bad coupling with the orbital 1, S0, of a proton. But there the phosphorus of period 3, so of course, therefore, it has 13C2P3, and it has that, but the problem is that this electronic pair here, this orbital, is very large, and it is badly coupled to a proton that is of the type 1s0. A proton is a small orbital, so when the clouds are of different size, as they do not fit well. Well, and before I finish, so that I do not know who is there with the basic really surprising cases that when one sees them I have it here scratched. I saw it in organic chemistry too for the license. There are some molecules, and they sell them. These are commercially available. In fact, the one they sell here in Chile seems to me that it is the one of True Singer. They are quite expensive, by the way. And of course, look, for example, this is the first one. The base of seeing each one has this basic phosphorus. And why is it basic? Because look, when the positive charge is protonated, it has 3 or 4 already. 1, 2, 3. And it is here 4. Then you have seen those balls that children play. Like this, it is moving the same, but at a molecular level. As well, the thing is that it has all these possible resonances making the charge actually where it is. It is strongly dislocated towards the nitrogen, and the phosphorus is neutral. That is why a base so strong that its pKa is very high, around 3029.6. That is super basic. The same here, it is the same, only that this is open, this is not cycled. We have that this nitrogen here has several possible resonances. Then the nitrogen is protonated here instead of the phosphorus. Think, of course, when the nitrogen is everyone is going to attribute to the nitrogen. Of course, here in the second case, the nitrogen is protonated. At the top, the phosphorus is protonated. Then the top is the example basic phosphorus. But in a very rare case, very well. Now, we return here to the tip. And then now with this in mind, and tell you already within the structures that we were seeing, here, 2, 3, 4, 6, 7, because the 5 is skipped, because the 5 does not have any. Then there is some that you see that it has an acid group. Already perfect then. The structure 3 that is here has a carboxylic acid. Question, and someone can say, well, the phenol is also acid. That depends on why at the physiological level the pH 7 does not take out the proton, because the Pegasus of a phenol is around there, near 10, around 10. And in fact, this may be a little less already, due to the effect of the carbonyl here adjacent in the structure, and apart from that, fluoroazo, that they exercise an effect at a distance in an inductive way. That does not manage to take out the proton from there, and that one has an acid. And then what else too after? The 4 has nothing, the 6, neither the 7. What happens with the 7? But be careful, because look here, there is no 8. Good in the case of the 7, it is clear that these groups here are methoxy. This is basic. This is going to protonate to pH 7. It will have a positive charge, then a base. Therefore, the O made here was structure 3OK. Well, you know that like this, all the questions point to the same. Look, first observation here. In the first agent that we have for psoriasis, we have nothing. There is no ionizable group. This is a neutral molecule. Then, only some functional group questions, because they already know that they have to name, as it is called, a cyclic ester. And this structure here is an ester, and it is cycled. Then, when it is one, almost not true. When one, we have the M-acetyl, but this is a cyclic ester or lactonin. And it is good to add some names, and these others that are here are type oxygens. That functional groups are those open or cycled. Very well, this structure is super little soluble in water. Last week we did the exercises where we saw if something was going to be able to solubilize A2. We said that they actually contributed very little in the table. They are over. Contribute is quite peri to solubility okay. And this molecule is great, and this molecule. How many chiral centers do you have that is also relevant? 4 to 1. 3, 4, 5, very well, because that center is not this carbon that is here. It does not have a symmetry plane, and then there are 5 chiral centers, and we go to the next. This antiparasitic says here, and which nitrogen is basic, the NH, this one that is here, which is a secondary amine. This is also a secondary amine, but they are different, which is the most basic of the structure. Perfect, very well then. But what would be the most basic then? The first one, that is conjugated by resonance with the benzene, or the second. The second, very well, the second basic atom of the structure, and that is important when making our docking, our analysis with E. The protein, by how much that is going to have a positive load, then that is basic 9 to 10 okay. That nitrogen, the other, not also the other, has the inductive effect of the nitrous group. The nitrous group is an electric attractor group. The nitrous group confers what type of toxicity the molecules remember. Exactly, very well, and in this antiparasitic, probably, that nitrous is activity. If you do not want to kill a parasite worm, it is good that it induce toxicity. Very well and well. Here we did the analysis, and then we are also going to stop at E. The intermolecular interaction and the relevance. Look, I can show you the atom of fluorine is surprising. In fact, there is a review that talks about that issue of the importance of fluorine in medical chemistry. I do not know if I am going to take this note, but yesterday a colleague told me look at the results, and he put the results following of a molecule that we were measuring the compound 1 to see how the thing was the compound 1 to see where it is the compound. One says it already has a certain effect, but a very high concentration. 100 micromolar is a very high concentration, but the compound 2 inhibits a drug. This LND is a drug. And when one of them is destroyed, yes, of course, then this is drug, the unit of my age. These are the molecules that we facilitate to some colleagues who work in the United States, and it turns out that if you look at the compound 1 of a chloroatom in meta, and it was not active to more than 100 micromolar activity, but see the only a chlorine biofluor made this molecule. If it had activity, then an atom makes a big difference, so to see the importance of functional groups. And now, of course, the challenge is to give an explanation to that. Here it is. And I think it has to do with the fact that a hydrogen bridge is needed, and not a logical one, but that we are going to explain when we see intermolecular interaction and molecular form. There is nothing either ask why these. Okay, exact they are friends, and they have resonance that never goes to protonate. Remember that the amidas are conjugated by resonance. Well, example 5, that you can tell me about this, it says. Anti-neoplastic, okay. And here you can tell me about this molecule first. This molecule is, or Carol, that you can tell me about the symmetry of this carbon here in the center of the thia. Structure, very well, because the two halves are not the same, because it has the chlorine for this. So exactly there, such that it does not have any ionizable group. These are two chlorina combined in carbon. So it is quite neutral to pH 7. Estradiol female sexual hormone is all quite neutral because no hydroxyl is ionizable, and this is saved. The phenolic, oh, this is phenol was already at 10 and an alkylic. Oh, this here. "16, and then it is good to remember those numbers because we are going to use them. None of them will be ionized to pH 7. There is no release of protons, and it has happened to us that sometimes when does computational studies, one sees the loads and the loads places arbitrarily the software, so you have to be very, very careful. Very well. And that molecule we already... What happens with these two? We go here, the 8 and the 9, and the 9 is not true very well. Then here, if we have possibility, this is a basic nitrogen, and we are remembering element general nomenclatures. The name of this ring is the starts with Pi, and very well piperidine. Perfect, very well the other alkylic hydroxide, so it does not have any ionizable group, the law. Molecule number 8. Perfect. Then this super good exercise, and for the functional groups, the different values of pK, sub A that they have. And this compound says already basicity the same. Here and then it says asymmetric carbons, and this is nothing more than the same, but with a slightly larger molecule and complex. I told you that one of the challenges for you throughout this course is to absorb the largest number of possible pharmacophores of small molecules, small responsible of the activity in this I mentioned to you. I think the first class or something. Perfect then. This is not the penicillin, but if it is similar in a porine cephalosporin, and the penicillin, the ring next to it, is 5, this ring is 6. It is similar. It is already similar. But it is not the same. But if having a beta-lactamic system, that is, it is a lactam that is A. Lactam acyclic amida. We have there a lactam. Then this lactam has alpha carbon beta. This lactam is cyclic. Then a beta-lactamic ring. This is inhibits the enzymes necessary for the synthesis of the cell wall of the bacteria. In what way they inhibit something very particular happens. It turns out that in the case of the beta-lactam, that you believe this ring here of 4, this little square, as its angular tension high, or low, very high, that ring is bursting, because it is a ring forced to that square structure. Forced to angles close to 90, being that in reality the angles should be deep, for example here in the carbon fiber 120, very well, one should have an angle of 120, but it has more or less 90, then it is. That it bursts this thing and more above that you can say, well, but what happens with the resonance? Does not have resonance. The electronic pair of the nitrogen is not conjugated in resonance to the carbon fiber by angular impediment. No stereo impediment when there is a spatial disturbance, a shock of atoms in space here, is that the nitrogen remains at such an angle with the electronic pair looking out, preventing that electronic pair from going to resonance. Okay then, if it does not have resonance. If it has to be, and of course, and in an appropriate angle and well, in the last class taking advantage of that you call us, they are going to install these programs that I can capture the full screen. I am not going to draw the whole molecule so as not to lose, but look how, for example, seems to be the zephyrdroxylum then. Look at a form, but I take the opportunity to show you something new today. I mean, at a computational level, you know the pumpkin site, that is where. There are many molecules at index site American or Gringo where the guys here have many molecules indexed. Almost all the drugs are here. Then if you look for the zephyrdroxylum, you look here, it appears immediately. Copying the smiles, that is this linear code for the molecule. Then it says zephyrdroxylum. We copy this smile code, which is a linear way of writing, and paste it in the chem as is, and so they do not have to be drawing structures, maybe for a report, something like that. They have a presentation in PPT. Or what will be masterful then, here is the zephyrdroxylum. Well now, I am going to take it to and we are going to make a small, fast molecular optimization here of, that is, the Newton laws are applied to minimize the organic structure, the Newton laws. As if these were spheres connected by spring, and we hope that it ends, and now we look for the mole. Beta-lactamic ring. And look at the following. Then, of course, this ring is not true good. The desire has the sulfur that is, as it is, twisted. That is, this spatially, and the electronic pair, if we could see it, would be like here. Okay then, that electronic pair will not be able to bend to enter the resonance. And what does that translate into as the electronic pair? And look here, is that here comes the key part, as the electronic pair cannot provide the charge density to the carbon. Only prime. In this case, the electroattractive effect of a negative electron atom, nitrogen in other words. The question is, in a beta-lactamic system, what do you think? The electrophilia of this carbon is greater or less than in a common carbonyl. This is a carbonyl group. Imagine a common acetone. There is no resonant contribution. It does not deliver electron. That is, it delivers less electrons. Already, that is, it has greater or less electrophilia, greater electrophilia. Very well, perfect, those are the key concepts. And then now we can go back here to the very well. And then this carbonyl, and here we are doing pure medicinal chemistry, since it is two. Explain the reactivity of a molecule at the biological level. It has an exacerbated electrophilia, an exacerbated delta, plus, that is, a lot of positive charge density, or vice versa, a great electronic deficiency, a high electrophilia, high delta plus, and of course, but in groups it is not true that they are highly toxic, such as acid chlorides, the anhydrides that we explained in the previous class. But at the back, because this now reaches the bacteria, it is not true at the bacterial level, as that carbonyl so much electrophilia, it is going to join the target. That are the enzymes that synthesize the wall of the yeast. Bacteria called transpeptidase, and these transpeptidase are proteins that link penicillin. Have a lot of serines, and the serines have what is the residue of a serine. And we are going to have to review the amino acids. It has hydroxyls then, as there are several then. Serenes in the transpeptidases of the bacteria, they attack nucleophilically to the carbon, and they are covalently linked, and this beta-lactamic system is going to open because the C sigma type pair migrates over the nitrogen atom, but it will be covalently connected to the transpeptidase, preventing its biological activity. When covalent is altered, its chemical structure is another one, and it loses effectiveness. And mechanism of action of penicillin. And ask then, you will never forget that when you see this little square, you decide on an antibiotic. Yes, very well. And now functional and ionizable group. Functional and ionizable groups here, amida, and this is going very well. That is going to be protonated pH 7. Yes, it can be protonated. No. It does not have enough bases to protonate, and there is. First of all, that the hysterical impingement that is as hidden in the middle is not true. Difficult to protonate it is clear. It is like between me, yes, very well. And as it is here, it loses the proton, and it will be with net charge, perfect as these molecules. Exactly the net charge is 0, but they have positive and negative internal charges. They can be several. But the total, the sum of charges, is equal to 0. That is called Schweiter ion. Question. We want to have pharma with Schweiter ions. If not, what do you think in some cases for? For activity effects, it is convenient. But at the level of absorption by oral life, that the intent at the level of absorption by oral life will be the Schweiter ionic molecules will be easy to be absorbed at the intestinal level, that we tell you in general. Yes, of course, in general, the Schweiter ions are not very well absorbed. Okay, then. They try to avoid when one designs pharmaceuticals. It is that it does not require a... So they seek to avoid as a general rule. Well, with that, we have finished then this first workshop of activities. Now we are going to go to the one of pKa. Okay, then today. So we finish. Now, with numerical calculations, particularly with calculations of percentage values of ionization that are super relevant for a statistical analysis now at the molecular level of what percentage of the molecule is ionized, then we are going to take the following molecule as an example. Look, this molecule that is here, figure 1 has a structure that if you see it in a large stretch, it is an aromatic ring, a polar connector and a tertiary amine. Then the pharmacophore is an aromatic ring, a gay connector or linker, and then we have a tertiary amine. Not primary or secondary, tertiary it has to be. When you see that pattern, you immediately, you say that is a local anesthetic then. What we have there is a local anesthetic, another local anesthetic. You know this is not the most already. This, I think, lidocaine. In fact, it seems that there is the name or not. It says it is an injectable blah blah blah, and it does not say. That one does not say anything, or that may be below it does not say anything. Of course, in fact, there is where they act, and we are going to explain something. And this is the lidocaine. Well, famous is the procaine. That would be the same. And the procaine has an ester here, and then it has 2 carbons. It has the tertiary nitrogen, and it has a nitrogen here. That is, it has an aniline in the structure as you can see it. Is similar, only that there is an aniline called the aromatic primary amine. Then we have an ester. The connector in this case are 2 carbons. And then we have the tertiary nitrogen. Connector is relatively variable, but up to a certain range. And here the connector is a carbonate 2. Here the connector is 2 carbon. Obviously, there is a range of tolerance. It cannot be very long because we lose activity. Then there is a certain margin there for 2 atoms as maximum. Good again, the aromatic system pattern polar connector in this case, an ester. And finally, they're not true. The tertiary nitrogen average lifetime, when I say average lifetime, I mean the time it takes to degrade half of the drug in the body. And now, but there's that the thing is out there. But that's why this has an ester, and this has an amida. So I repeat again, which has the most average lifetime, which survives the most. Amida, very well then. The amida has a longer average lifetime. The enzymatic degradation is more stable. The erases cannot degrade it then. Bad, good, depends. If I want a short-action drug, I use the ester. But the action to be longer, I use the amida. These amida are used a lot at the dental level when one is going to do a dental treatment. Because anesthesia is generated in the gum prolonged instead, the ester would have a shorter effect. That is why some esters also occupy themselves in anesthetics of gums for babies, where what is sought is simply to momentarily reduce the bite when the teeth come out to a guava. Then it will depend. Not true. That is what one seeks, and going to the structure, it is clear to us that the tertiary nitrogen will be protonated AAF7. That nitrogen is the key point then of the analysis that is going to happen. Below we are going down here now, and it turns out that good if we compare this, for example. Look at this molecule, the procaine, the lidocaine. There are several of these. They are all very similar with this pharmacophore. But if you come with this, look at this. Here is the diethylic ether. Or dry the ether was occupied for many years as a general anesthetic. So here we introduce a new concept while the right ones are local anesthetics. And what is the difference then based on the structure? If you compare the letter that simple molecule, that an organic chemical solvent, all the laboratories where you have to dissolve something in a polar solvent, the letter is not soluble in water, but the letter is super volatile. Then the difference now is not occupied because there are better alternatives, less. If perfect, it will reach all parts. They do not sit, including the brain. Falls asleep when he breathes ether. The other is loaded, and on the basis of that, there they are. Doing a reading of the chemical structure, they will have the same action mechanism. No, we are going to say that the structure with the pharmacophore has a specific action mechanism then. These are called specific action mechanisms, while the molecules that do not have a particular target have an unspecified action mechanism. There is no protein in particular. Whether the diethyl ether acts, you do not even know how then. What is the effect? Because for there to be good conduction of the nervous impulse, it is required that the myelin vein is unaltered, and what the ether does exactly, it alters the membranes, it disturbs the electrical conductance of the myelin vein of the neurons, that is like this, bathes the myelin vein, because it is super lipophilic, disturbing the proper conduction of the nervous impulse. Already in the time of the Khoi, it was very fashionable that they were selling on all sides quaternary ammonia. They remember the quaternary ammonia. And I even read companies that went to the chancho, so to speak, and people passed through a door and they were sprinkled with quaternary ammonia. That seemed a bit exaggerated to me, but hey, look at the quaternary ammonia is a generic term. There is no pharmacy, so it is called quaternary ammonia. That is the name of the functional group. It is clear. A quaternary ammonia, if we saw it very well, it is any long chain salt, okay. It can be longer than that with a positive nitrogen, and as a contra-ion for the general, something economic like a chlorine atom. Then, is that a nitrogen with a positive net quaternary charge? Is with permanent charge the loso-organe Fe7 charge, and that has a bactericidal effect because mechanism. This is like a lipid, like a soap, and in specific, that is again, it does not have a particular target. It does not inhibit the transpertious protein, but it alters the membrane of the bacteria, and the bacteria bursts today. So it is nothing more than a topical, superficial, physical, chemical effect of surface, is not a specific effect. So there we do not talk about the fact that there are certain pharmacophores to join a protein that does not. So it turns out that for the local anesthetic to have an effect, there is a small inconvenience. It has to join the sodium channel to block it so that there is no transmission of the nervous impulse. Here we can see a membrane. This is a very simple drawing that the only thing it does, that when there is transmission of the nervous impulse, what happens, the positive cations called sodium enters. Remember that the neuronal membrane on the outside is positive, and on the inside, that is normal in the basal state. Then the depolarization of the membrane massively, the cations enter, and an inversion of this capacitor is produced. That is, it would momentum outside, and here inside positive on this side, and for that sodium travel through the sodium channels. Well, what does the local anesthetic enter the neuron? And inside it joins the sodium channels with positive charge, blocking the entry of sodium cations. Then the problem is this one that has to enter to be able to have an effect. It cannot join the channel outside, so it does not work. It has to join inside. Inside is the question is how it enters, if it has a good charge, because since it is a tertiary mind here, there is a balance. Exact part is a percentage. As there is a balance, it means that at some point, obviously, the balance is more displaced, where to the protonated form, there is more of the protonated form, but at some point we are going to have that there will be a certain amount neutral, and there the membrane passes through. Passive diffusion, and inside it, protons again, and in a positive state, it blocks the sodium channel. Then now what interests me is that we are able to say this is going to be protonated, it is going to be ionized. And in what percentage it is going to be ionized? We are going to do this type of functional groups. Then we take some of this, one should be with some value. Here we have 2, then we are going to do this analysis while we have a comparison of those butpidacane. See how the pharmacophore is repeated. Aromatic ring connector here. I have the connector is the amida, a carbon and tertiary nitrogen. The same here, okay. The same is the only thing that changes is that here the chain of the tertiary nitrogen is shorter. Observation already asks, which of the two is more lipophilic? Nothing more than seeing the structure perfect. The first? Very well. Then the first is more lipophilic, exact, major log P. It has less. Second question, that means that the first is going to be more protonated than the second. There is no relation. And so very well, it has nothing to do with the pKa, with the log P. They are different things. Not because something has more log P necessarily means that it protons more. They are different concepts. You cannot mix them, and what value of the log P will have this from 2 up, I think, already, because a fairly lipophilic molecule, the other someone can say, but it is protonated, it gains a positive charge. It has no relation that something is protonated with that its log P disappears or goes down. So, also be very careful, they are separate concepts, and if we could see last week, I told you that there was a website that was blocked, but they reactivated it. You know what it was called? It was called Mole. And around there it goes like this. Exactly, let's see here. Mole and all together. pKa. Well, we occupy it. I do not know if now there. Look, you can paste the molecule in Smiles format. Therefore, what was the first? Bupivacaine drug. And then to not be drawing it, then we come here to the structure. And we copy direct and we go here, you paste it, or give click here in Droid and Droid already. Predicted, there it is. And then now I want to see this value look at 8.4. I do not know if that is what is reported. 8.1 says in the tip. This is a calculation, but second observation. Ask what this marked in red means. Here it says acid base acid. Then it says base. That is what this is saying. That protonation can be done well. That is that value that you see here. 13.9 is the value of pKa. Of this neutral proton, that is, I need a base with a pKa greater than 13.9 to start that proton. What is the physiological pH 7? Therefore, to pH 7, this proton comes out impossible, it will stay. And then that with respect to that, and from there you can predict the mepivake, and we return to the tip. Well, this part now is crucial to see. Always work with pKa, not with pKb. The most normal thing is to always work with pKa. So what we are going to do is an analysis of degree or percentage of ionization. And we are always going to be talking about pKa. Then, for example, when we think of an acid, then we go to number 1, the first case, the case of an acid drug, the acid drug neutral part. The acid drug releases the proton we can. Understand the equilibrium in this way. It releases the proton, but the incorrect thing would be to say that the acid drug delivers the proton to the water of the medium. One would have to write here H3 or more, or hydronium more to less, although that is the respective anion is formed. Then, the acid drug is the one that delivers the proton of some neutral functional group. We start with a species that at the beginning is neutral, and this species generates an anion. Okay, and that anion is the famous conjugate base. And how is the equation that describes this process called the Henderson equation? So, we are going to see now the Henderson equation. The Henderson-Hasselbalch equation in its logarithmic form, any process of this type is quite simple to describe this. You know it from general chemistry. The constant of R. This is equal to products in molar concentration divided by reactants. Then here I am going more or less dynamic because I know that they already know this, but I have to give then the only thing I am going to do there is to rearrange this a bit, and we are going to apply on base 10 on both sides. And we are also going to define less logarithm for the function p. That less logarithm is the same as saying apply logarithm, and then multiply by -1. It is not true. It is like saying -1 multiplied by the logarithm of something. That is, it is an ultra-simple operator. Well, then applying less logarithm, that would be like pk sub a equal, and the concentration, remember that this is always molar concentration, the least logarithm of the proton concentration. We are going to abbreviate it as pH minus logarithm of the concentration of a minus divided by half. And then, there we have the equation. In its simplest form, pk sub a is equal to pH minus logarithm of a minus divided by half. Then what do I want to highlight here? that in the case of an acid drug in the numerator, we have here to the right this a minus that would be the neutral form or the ionized form. Perfect then. That is the ionized form of the drug. That is what interests me here. Is in your mind in the numerator, we have the ionized form in the numerator is the ionized form. Well then, that does not have anything complicated for you. Just say one small thing more, only that also if one wants to rearrange this, you can rearrange it as molar concentration of A minus divided by concentration of Ha is equal to 10 raised to pAc minus pK sub A. That is clearing the equation. That would be another form, the exponential form of representing this equation. And so nothing new, only playing a little bit with the numbers in a very, very elementary way and two. But then you will see of some things that will probably not be remembered. There we are going to explain something else, but 2-second case, the case of the basic drugs. Basic drugs, you already know that the basic drug is a protonable mine then. Basic drug to release a proton as it has to be, because it is a base. If the bases do not have protons as the basic drug can release a proton. When it is ionized very well, then we start with a structure of type NH+, a structure, ammonia, which at a generic level, we are going to abbreviate it as BH plus basic protonated positive charge. This is my starting point. This is my acid. Now that releases the proton, and we are going, therefore, have a proton and the drug in a neutral state. Okay, then the drug in a protonated state has a dissociation balance, so to speak. And now to the same story again here. There's nothing new. Case A is equal to H plus by B divided BH plus. Here I am going to skip a few steps, because this is nothing more than an elementary mathematics. Apply less logarithm. I am going to write the result immediately. Then the final result would be left as pK sub. I meant pK sub A equal pH minus the logarithm of the concentration of B divided by the concentration of BH plus. And then I do not want to erase the other equation. That is why I apologize of the image there. I have now the comparison. Then now ask, where is the bow? Drug in its ionized form in the denominator is reversed here. We have now the drug in its ionized form. We have there the drug in its ionized form. It was upside down, and therefore now the exponential form of this would already be not certain clearing, B divided by BH plus is equal to 10 raised to pH minus pK sub. These are the two ways. This is the exponential equation. And above we all exponential equation, and with those we can work from now on. So now we are going to be able to know what happens with the different functional groups in a complex structure that is applied. These simple equations, the pH 7, unless, for example, we want to know what happens in the stomach, and there the pH can be up to 0, even right, very acid, 0, 1, 2, and no more, because if the acid in the stomach goes up a lot, we get sick. The intestine, pKa, for example, in the intestine, it can reach up to 8. As is, or the duodenum when it comes out of the stomach, the first portion, and there it can have a pA more or less of 5, 5, 6, and then it becomes 8 in the average course. If the absorption is different depending on where we are, okay, very well, then now we can do our analysis with this, and do not forget what we had explained a couple of days ago. Positive that was this, our equations. When you have a pharmacy, then now, 2 relevant cases first, and then if you have an acidic pharmacy, if you have an acidic pharmacy, okay, we are going to have to do the subtraction. If you do the subtraction, if the subtraction of pH minus pK your age greater or equal to 2 units, you will automatically say that the pharmacy is 100% ionized then. A pharmacy that is 100% anionic in that case, while if you have a basic pharmacy. And now we have to think right, the pharmacy is the other way around you. Well, if pH minus pK your age good, in this case, we could be more purists here and say that we need to take or do the subtraction the other way around. Okay, here, let's do the subtraction the other way around better so that we are positive, and I apologize, they do it the other way around. pK your age minus pH. If pK your age minus pH gives you greater or equal to 2, what happens? There we also have the pharmacy 100% ionized already. But it is not going to be confused then when we talk about ionized case. It is the anionic pharmacy. In the second case, it is the cationic pharmacy. Why 2? Where does that come from? Why not 2.5, 2.35? Because exactly, it is 100 versus 1 as is, and we can show it with the equation. Excellent. And then we go to the case of the bupivacaine. You have it there in the cow tip. I go back immediately to this. I just want to see the value that they give here to work with. Value of the tip. It says that the bupivacaine is 8.1. And then we go there, and the first problem then. The bupivacaine, then the bupivacaine is 8.1. That is the value of pK. Your age, therefore, the balance that we are seeing here is the balance B plus H plus then we would have the equation of the following way. That goes in the numerator, short-term memory. That goes in the numerator, the neutral form, the ionic form. Very well, be divided by BH plus is equal to 10 raised to short-term memory. Perfect, very well, pH minus pK, your age. Then I have here as 10 raised to the pH 7, not true the pH. In this case, cell enzymatic well of the enzyme. They inject the anesthetic enzyme minus the pK your age 8.1. And there we apply the calculator. Quickly there to see what exact value. That of course, yes, then we have to raise it already then 10. Minus 1.1 to see 10 raised to minus 1. It will be like this. It seems that no other way around. I thought this. 1.1 negative. And now if I apply the 10 there, if 10 raised to minus 1.1, it gives me 0.079. Yes, already. 0.079. Then 0.079 is the ionization percentage. Is the proportion very well already? Sorry. There is the point we have not yet calculated the degree of mole ionization. Because of course if you want what happens here, if this one is divided by 1, and that is the key, I am going to say conceptually speaking that for each ionic molecule there is 0.079. Nitra is not true, and then, but that is not the degree of ionization, because then I say I reached a certain proportion, and how from there we come to say there is so much % ionized. We will have to transform that now in the following way, but direct our look. What happens is that the total of molecules we are going to do this reasoning, the total of molecules is equivalent to 100% to 100% of what of molecules is not true. The total of molecules is 100%. What is the total of molecules? 0.79 or 1 or the sum perfect. That 1 plus 0.079 is 100% of molecules. And now I want to know the degree of ionization. Or I want to know what percentage is ionic. Therefore, what do I have to place here in the phi? Numerator. Very well, because 1 is what is ionic. Well, now we multiply all this thing and see how much it. So we apply a calculator quickly that would give us a certain 100 divided by 1 point. But the fraction thought the fraction measured 398. Yes. Now 6 to see it says if 7.6, the MEPO came to 7.6. And I was wrong then. 25, thanks, okay. 25 is 1. And then now you apply the famous rule of 3, but the total all is 1 plus 25, and perfect.